I changed slightly the title. The quantum part was deleted when I realized that I had Guillemot as a chairman. So anyway, for lack of time, I just decided to speak about the first part only. Second part, I should speak about it next week in Cambridge. And about this talk too, I apologize for the people who were in Cambridge in January, because that could be quite similar, yes, to what I talked about there. So it just in joint work with a group of mathematicians in Orléans, Michel Zinsmeister, and some students of him. I take the opportunity to, this has nothing to do apparently with the subject of the conference, of course, which is in remembrance of Claude Itzykson. But recently, another tall figure of physics, Sam Edwards, passed away in Cambridge. And for people who were there at this time, in the 80s, Sam Edwards was an important figure in polymer physics. And I just recall you the famous names like Paul Flory, who got a Nobel Prize in chemistry, Pierre-Gilles de Gennes, who we all know, who got a Nobel Prize in physics, and a senior member of this lab, Jacques Descloiseau, is still fortunately alive. So there was the three, so Pierre-Gilles de Gennes, Jacques Descloiseau, and Sam Edwards was really somehow about the same generation and just somehow laying down the foundations of the physics of polymers. And polymers, of course, is lurking behind, SLE. You heard about SLE today already, Schramm-Loeffler evolution, so I'm going to address this subject. But in a way, there is, among all the SLEs, these two-dimensional processes, there is one particular one, which is the SLE 8-third, which is supposed to be the scaling limit of self-folding walls in 2 dimensions, which are the model of self-folding polymers. And of course, there is a long way from the standard physics of polymers to SLE, not completed yet, but somehow should be completed in the next few years. Let me move on, and so I just, with the first slide, I put serendipity that doesn't seem to please Mireille Buscanelli. So I'm just put this word here because somehow we discovered some properties of the SLE, whole plane SLE, starting by studying something which looked like Iniocuous, which was the Taylor expansion of the SLE holomorphic maps function. So in general, you have, if f of z is an holomorphic function in the union X, you assume it is injective. Then there is a famous conjecture, and actually final theorem by Bieberbach, that first the first position is non-zero, and then A2, the AN are all smaller than n A1 in modulus for any n. And so Bieberbach proved that for n equal 2. It was proven for n equals 3 by Loeffler, and the conjecture was given by the intuition that the Kuebel function, which is simply this function, which is a map bijection between D, the unit circle, unit disk, and the complex plane slit by half line, should be extremal, because for this one, n in modulus is n. So this conjecture was finally proven by Bertrand, and the earliest contribution to the proof, actually, was that by Loeffler, where he invented the Loeffler equation for that, to this aim. And then he was able to prove that the modulus of A3 is smaller than 3. And actually, the Loeffler method, as you know, was revived by Schramm, where he introduced randomness into the equation with a source term which was given in terms of standard Brownian motion. So let me move to whole plane SLE. So the equation here, for the whole plane, the equation is of this type. So Ft of Z is your differential map, is your holomorphic map, depending on T, and it's driven by this equation, where the source term lambda T here is given on a circle here, because you are on the unit disk, by the exponential of the Brownian motion times some coefficient, which is traditionally written square root of kappa. Actually, the whole somehow setup of this approach can be generalized to Levy processes somehow. So for the sake of generality, I kept Levy process at the beginning of the talk. So typically, if you have a Levy process LT, its characteristic function will be given by some Levy symbol eta of psi. Psi just is coefficient of LT here. And in particular, there are the alpha stable ones, where the theta of psi is given by this kind of function, modulus of psi to the alpha. And here I normalize it with kappa over 2 in such a way that for alpha equal 2, which is the case of ground motion, where LT is simply ground motion, in that case, kappa will be the same kappa as here. So anyway, we have this kind of chaotic function, this kind of Löwner equation, Schramm-Löwner equation. And for the whole plane, we are going to go from the unit disk D to the whole plane slit by the SLE curve, which will be infinite, unbounded. That will be the key property actually of this study. So the drawing is a bit like that. So you have the unit disk, you have the, of course, the unit, you have lambda t, your source function, which was here, this one, and at time 0 it's at 1, and then you have a map from the interior of the unit disk to the complex plane, slit by a trace, which is a trace of the whole plane SLE. At time t, the tip here, gamma of t, is just the image by ft of lambda of t, the source term. And at time 0, gamma of 0 is just the image of 1, because this lambda of 0 is at 1. And then there is another point which is important, which is a random point on the unit disk, the circle, which is the pre-image of infinity, because there is one point which is sent to infinity. And when time starts, so time flows from 0 to infinity, and when time flows, somehow your tip recedes. So you erase, in this process, you erase part of the curve, like indicated by this dotted line. Okay, so why is that interesting? Because first of all, ft, suppose you have ft, the solution of this equation, then if you write exponential of minus t ft of z, it tends to grow with time, and then you renormalize it, rescale it by exponential minus t, and then you expand in terms of t, of z. So you have this Taylor expansion, and the point is, so here I just took a Levy process, LT, of course, ground motion. And then there is an invariance property. Of course, everything moves with time. There is a kind of invariance property, which is that if you take f conjugate, meaning multiply ft of z times exponential of I lt by this one, then it has the same law as f0 of z. And it means in terms of the expansion here that the coefficient an of t multiplied by this exponential factor are in law the same as the coefficient at time 0. And so there will be something which will play a role also later, which is what is called the modified version of this map. So you take ft at point z square and take the square root. And if you want to have a good definition that z equals 0, so you just divide by z square and re-multiply by z to have the proper branch. But essentially the square root of ft at z square. So it's called the modified version. And there is a kind of n-fold version that we will see later. This kind of standard procedure. And it was important to consider this kind of maps was important for the proof of Weber-Bas conjecture. So if we just take this kind of expression, then there will be also a conjugation result, which is that the image ft second 2 taken at this conjugate point multiplied re-multiplied by this actually is the same law as the times 0, 1. So it means that of course the property of this kind of functions is that it has an expansion only on odd powers. And so if you call the coefficients b to n plus 1, the b to n plus 1 of t in law multiplied by this will be the same as the one at times 0. So it means that really if you want to have access to the properties of the map, the random map, it's sufficient to work with the time 0 method. So what is Löwner's method, which dates back to the 20s of last century? So you have ft, which is expanded like that, and then you have an equation, which was Löwner equation here. You expand, so of course you have ft here, you take the derivatives and you expand term by term, and then you have a recursion, of course, which is of this type. So the dot derivative of an of t, which means the time derivative here, is given in terms of an and the other coefficients for k from 1 to n. And of course, so you have these simple coefficients, which is k times the conjugate of the source term, which is lambda bar here. Lambda which is 1 over lambda, since lambda is on the unit circle. So you have this kind of simple equations which somehow run the show. But of course, you would like to extract some information from it. So one first thing you do is just calculate the expected coefficient. So I won't spend much time here on this. So if you take, so of course, now I call an the values at time 0, because I know this, that is, this is sufficient as an information. So the same thing for the bn, for the modified map. And then you find this kind of simple factorized forms. In terms of this Levy, you remember, there was this, for a Levy process, there was a Levy, the Levy symbols, which are the eta of k are just the values of the Levy symbols at integers. So you get this kind of form. So this is not difficult to get, but of course, because they are factorized, you see that if sometimes the eta of k happens to equal k plus 2 here, or here k plus 1, then the whole set of coefficients, when you go up, go to R0. So you get very simple results. So for instance, if eta 1 equals 3, that's a simple condition, then you see that the expectation of your derivative, which you get from the coefficients, is simply 1 minus z. If you take eta 1 equal 1, eta 2 equal 4, you will find out that the expectation is simply this polynomial. And if you take the modified version, again the derivatives, I'm taking the derivatives because they are going to play a role later, a crucial role later. Of course, at the same since they are power series, you are going to get this kind of explicit result. Here I mentioned in parentheses that eta 1 equals 3 actually is valid for a particular example of SLE, which is SLE 6, which is the SLE which is giving the scaling limit of percolation, the boundaries of percolation clusters, for instance. SLE 2 for eta 1 equal 1 and eta 2 equal 4. Actually, you could think that this is a broader result. Actually, it's not. If you have a Levy process with these two conditions, and because of the Levy-Khinchin result, you can show that actually it is necessarily SLE 2. And for SLE 4, which we have eta 1 equal 2, and then we have a simple result. Again, this is simple to get from the equations, and I'm not going to spend too much time. Where was the serendipity? It was when came the idea from mission this myself to look at the expectation of square of the moduli square. Here I actually, by the way, mentioned Campaignen, who actually looked at the expectation of higher moments, but without moduli. And the difficulty came, or the interest came when we looked at moduli. So the surprise came from looking at expectations of modulus of an squared. So this was done here up to n equal 8. So these curves corresponds to different values of, so A1 is always 1, so of course it's green. This is as a function of kappa, between, here 5 and 7, say. And you see that all of these curves as a function of kappa for all of this n from 1 to 8 just intersect for kappa equals 6 go to 1. So if you go higher, 19 here, you have the same thing. And you have, so which will be for SLE 6, because this is again kappa equals 6 here. And you can, so there were another type of results we got by looking at the case of SLE 2. For SLE 2, if you look at the expectations, the expected value of an squared over n, you are going to see this kind of curves as a function of kappa, but they all cross 1 for kappa equal 2. So this was for any kappa, and for n again from n to 1 to 8. And if we just go higher in terms of n, we have more curves. N goes up here, and then of course they all have this same properties that for kappa equal 2, you do have 1 for this expression. So we just started a kind of experimental mathematics, just looking at what happens if you compute, and actually we did it first by hand. So by hand, if you compute, say up to n equal 4, you get something of this type as a function of kappa. It has a typical structure, like factorized downstairs, non-factorized upstairs. But here, so that was done by hand, just starting from the recursion of the recursive solution of the Löwner equation, Schramm-Löwner equation. But of course, if you put kappa equals 6 here, you are going to find 1. And so we did it by hand for n equal up to 4, by compute assisted formally up to 8, numerically up to 19, and then we stopped and we have to put it. So finally, it became a theorem, so that actually it's valid also for Levy processes. For eta 1 equals 3, you do have, which is the case of SLE 6, you do have this result. 1 and 2, which is SLE2, you have the other result I mentioned. And for the modified version, for the odd maps, the square root of f of z square, you do have this result also of the same type, that the expected modulus square of b is given by this form, as a function of f, so which is valid for SLE. I'm going to give you more results of this type. First of all, explain where do these results come from, and generalize them. So, trying to be a bit fast here. So, if you look at moments, it's not difficult. You get this kind of results. Now you are going to look at derivative moments of the derivatives. So, the whole plane SLE kappa map F0, which we saw before, has expected moments of the derivatives of this type for the simple powers, and for the powers of the moduli of this type. But not in general, of course, because this in general you don't know how to compute this expression, but for a special set of exponents, which are given by p as a function of kappa, which is this form, of this form. And then the alpha you get here depends also on kappa, as this, and the beta here you have depends on kappa in this way. So actually that kind of form was obtained, first by Lutsenko and Johan Oliver by a different technique, which was kind of iterated, done a bit numerically. And you will see, generalization of this later, and the way you can find this kind of formula, and the ways they actually embedded in the broader problem. So, for instance, if you have such a formula, so I will explain briefly how you get this kind of closed form formula. But again, this is valid only for very special values of p depending on kappa. And for instance, if you take p, if you want to have p equal 2, because if you have p equal 2 here, you are going to have the expected values of the square of the square of the derivative, the modulus of the derivative, meaning that by Parseval exponential, you are going to have access to the expected coefficient a n squared, which I mentioned before. So p equal 2 corresponds to what I described before. In that case, you will have if you take p equal 2, there will be one solution of this, which will be kappa equal 6 or kappa equal 2. For these two guys, you are going to find closed form formula of this type, which are just corollaries of this result here. So in these cases, you get these closed forms, and then you expand and you get this result for the expected values of the n squared. So we have generalization. I will, of course, this will be somehow the tip of an iceberg, because once you have this, you will realize it will be a discrepancy with some other results. But let's move on and look at a generalization of this, which will be, for instance, what is called logarithmic moments. So for instance, there are some very special values of these moments p, of this type, where you can calculate actually the expectations of ratios of the derivatives to the map. So again, it has this kind of characteristic functions, the product of two complex conjugate algebraic functions divided by this typical 1 minus z bar to some power. Same thing, this will be, for instance, here for p equal 2, you will have kappa equal 2 again. So here you have f power 2, you will have this closed form. You take the log of f0 over z from this, and then you will have an expansion, and then you will prove from that result that actually the expectation of gamma n square in modulus will be of this form. So it's just another example of what we had before. At the moment, for the moment, these are examples. You can look, these were ratios of derivatives to the map, to some power, and you can generalize, hence the title of the talk, generalized moments, meaning you can look at the expectations of ratios of derivatives to the p in modulus, to the map itself in modulus to the q. And for instance, if you decide that you want to have p equals 0 now, and just only f naught, unlike the previous results which were only for the derivatives, then you have again a special set of values of q's of this type where you do get closed. So, you also have a zoo of things, and you would like to understand exactly what is the structure behind it. And we have this kind of, this is somehow, from that perspective, the first general theorem we have, means that if you have these 2-point estimates, meaning the expectation of this expression taken at some point z1, this other expression, same one taken at some point z2 in the unit disk, it will have this closed form in terms of gamma here and beta, where beta is given by simply by kappa over 2 gamma squared, and this 1 point, hence, so we have this result. So if you take Z2 now equal to Z, you will have simply this complex, this 2-point result will collapse to a 1-point result here, where P this of this type, where you will have simply this form again. And that will be, you have this kind of closed forms, not only now at special points, but along certain parabola in the PQ plane. And that parabola is parametrically given by gamma, which is the gamma you see here, the beta again is given by this. And gamma will be simply given by this combination of P and Q. And this will hold true, provided the gamma is such that it satisfies the second order equation, which is actually this is parametric equation of the parabola. So if you draw it in the plane, these are 3 examples for different values of kappa. So these parabolic curves for kappa equal 2 in blue, kappa equal 4, and kappa equal 6, which are the ones we saw before. And you see that, so you have a special point here. You have an intersection with the p-axis, meaning q equals 0, which was the first case we had before, because originally we didn't look at the moments where you had q, right? We had only at the first, we started with the expectation of the moments of derivatives, like you do in integral mean spectra. But while here we have this extra parameter q, and so before we were on this q equals 0 lines, and the special point we had in the first theorems were actually the intersection of this parabola with the p-axis. And actually we have, for each kappa, we have a special parabola where we do have this special point. So, so how do you get this kind of results? Well, actually you use something which was done before for studying the integral mean spectrum of SLE. You use what is called the Belayev and Smirnov equation, which here I wrote in terms of cylindrical coordinates on the unit disk, which is f here. So you don't need all the details of the equation, but f is from here. For here I go back to q equals 0, meaning I look only at the expectation of the moments of the derivative for the moment. That equation was written by Belayev and Smirnov for the outer whole plane case, meaning a map from the outside of the unit disk to the complex plane slit by the whole plane SLE, and they had the parameter sigma here. So one simple observation consists in noting that in our case, when we are inside the unit disk, we just change sigma to from 1 to -1. So you sigma just tells you whether you are inside or outside. And it will make a big difference, actually, because the results we get are only for the inner map, so meaning when you map the inside to the slit plane. But anyway, they are driven by similar equations. And this lambda here is simply in the case of Brown motion, so SLE, this is just the generator of the Brown process, or in general it will be the generator of the Levy process. So this was in polar coordinates, and there is a better way to write it, which is in polymorphic coordinates. So again, f is given by this expectation here, and it obeys, of course, it's formally a function of z and z bar, and it obeys this kind of equation of a second order in z and z bar. And d and d bar, of course, which are the derivatives with respect to z and z bar. And sigma, so p, you remember, so what is striking that p, the moment is simply here, and the sigma here tells you which case it is. And here we have again p, of course, and sigma, and kappa. So you see kappa, which tells you which SLE you are looking at, is simply here. P is the order of the moment, and the type of whole plane SLE inside, sigma equal -1 or sigma equal +1 for the outside case. Actually, so if you want to have, so this is only for the moments of the derivative, or the modulus of the derivative, here for the time being. I have not put q yet. And if you want to have the kind of results I was showing you at the beginning, well, you study the algebra, so you just study the action of this operator to expressions of the form phi of z, phi bar of z bar, and p of z bar, which is a polynomial, in particular of this combination. And you inject this algebra and see what happens, and then you study the property of this equation, and it's not too difficult, of course, to get this result. But of course, you will get very specific results. Once you, but the interesting thing about these results you get, which I can briefly show you, in case, let me go back to the very first one here, which was this one, which we have only for P called P of kappa, which has this form, right? P of kappa will come back later, and then the alpha and beta have this form. The fact that then you have somehow the way this expected modulus of the derivative grows when you approach the boundary of your unit disk. So it blows up like with the power beta, right? And this power beta is the subject of the study of integrals mean spectrum. So in general, so let me go back to the definition. So there is something which is called the integral mean spectrum for these conformal maps, which is the function defined on R for in terms of the moment P, which is the lim sup of the log of the integral on unit circle multiplied by R when R is less than 1. So here you go to R to 1 by lower values. And so you just take the log of this integral divided by the log of 1 minus R. And then the power beta is just this lim sup. So here we have a stochastic map. So the first thing you would like to do is just to define the average integral mean spectrum, which is defined in this way. So you just put an expectation in front of the moment. So the betas we were obtaining for the closed forms were actually of this type, of course, because you had closed forms and they were just blowing up exactly on this way. In general, you don't have an exact blow up, but you have this kind of spectrum which you get from these definitions. And the interesting thing is that for the SLE, there were predictions, well, actually not predictions, theorems, in particular by Belayev and Smirnov in 2005. But actually, there were an agreement to earlier results done with theoretical physics methods. In this case, actually, with mathematical methods. And so there are two functions, one which we call beta 0 of P and kappa, and which is just given by this explicit form, okay, square root with P is here and kappa is here. And then there is also a linear spectrum in terms of P, which is this one, beta sublim. And these two spectra were supposed to give the spectra of SLE. So, meaning, in particular, the average integral mean spectrum, which is, the one defined here, which is simpler to get than the spectrum, say, almost surely, of course. And the average mean spectrum was given by the function beta 0 bar, which is either beta 0 when P is less than a certain value P star, 0 of kappa, which is given explicitly here, or later, after P star of 0, which is a positive value, it was given by this linear function beta lin, which is here. So that was a prediction from Belayev and Smirnov using the equation I showed before. And the interesting thing is that for the whole plane SLE we had, the version we had, the inner version, the betas you get, on the special point, P of kappa, doesn't, here I'm speaking only of the moment, the moments of the derivative. I don't have the Q parameter here. Here I just have only the P. The values we are getting at this special point, P of kappa, were not on this curve as a function of T. So these values of P were positive values of P of kappa, and they were not fitting this formula. So what is going on here is that actually there is a phase transition. So the whole plane SLE kappa and its n-fold transforms, which are of this form, right? A generalization of the case m equal 2 before. So you take f0 of z to the m, and you take the 1 over m's root, have average integral mean spectra that exhibit a phase transition, and for P positive, at least here, are given by the max of this Belayev-Smirnov function, beta 0, which we had here, and a new function, which is given here in green, which depends on P and kappa. And if you take the higher versions, like the modified one, beta of 2, beta of m, you are going to define, this is always the same beta 0, might be beta at when you, which is, beta, bar, which is the supreme of these two. But say, for the case for the simple whole plane SLE case, it is the max of these two guys, and it has a phase transition, so this one becomes bigger at a certain P star, which is of this form, which is actually happening before the P star 0, where it turns to be linear. So remember, you go from beta 0 to the beta linear at this P0 star, but actually before you get to this linear transition, you have another transition, which is this P star. And so this is the picture you have. So this is a Belyaev-Smirnov function, beta 0. Remember, actually, it had a square root singularity for the value p equal 4 plus kappa squared 2 over 8 kappa. So clearly, it could not be valid for high value of kappa, and hence the transition to a linear spectrum for the expected spectrum, expected integral mean spectrum. And here, so which is actually this square root singularity, and of course there is another branch here in red, in dotted red. So the claim here is simply that you have this. So in principle, according to the scheme they had, you would have a transition from the blue curve to some linear spectrum somewhere at P0 star here. Well, actually, there is another spectrum which is underneath, which is the green one, which is this form, which at some point before the linear transition actually supersedes the blue one and just gives the blue spectrum. And the special point we had in this closed form results, which could not be on this Belyaev-Smirnov curve, actually they were here at the intersection of the analytic continuation of the Belyaev-Smirnov function, after this point here, with the green spectrum. So here, this is a P of kappa where we do have a closed form. And this is just on this curve. So actually, so this is really, we believe is true. Actually, what we have proven actually is the fact that it is first Belyaev-Smirnov, then this spectrum up to this point. And after this special point P of kappa, so this is the next slide. So the real theorem is that for P less than P star, this is beta naught. Then you have this new spectrum, which is greater than beta naught, between P star and, in principle, P of kappa, which was here. But for technical reasons, you do have still a mean of this and that. And so on this segment, you do have this result. And then you have something which is, after that, up to P of kappa, you have something which is greater than this, or equal. And after the special point P of kappa, you have this result that the real spectrum is greater, smaller, or equal to this one. Actually, of course, we believe that this is a correct spectrum. And the fact that you do not have that in the Belyaev-Smirnov solution is the fact that for our version of it, of the inner version, they had the outer version. Their solution ceases to be uniformly positive. So you have something happening, and somehow there are techniques to try to prove this. It's a bit tricky, so because as we said, we could prove it on a certain segment and using a certain duality actually, which I don't describe here. And the whole thing changes after the special point P of kappa, where we do have the exact result anyway. And then after that, for the time being, the method doesn't work. So anyway, we believe this is the spectrum. And I would like to make so now there is, so as I said, that was for the unbounded whole plane SLE kappa, which is the whole plane you have when you map the inside of the unit disk to the slit plane. But the Belyaev-Smirnov, they had the outside of the unit disk to the slit plane. So it was slightly different version because it's given from the other one by inversion with respect to the unit circle. And for this one, actually there was also a hidden phase transition, which we studied with Belyaev last year. And it is given, so there is this just on a negative P. So here we were on the positive part of P, so we had this transition. But on the negative part of P, for their version, not our version, there is another. So this is the blue part, this is the beta 0. And then there is a new green curve, which is here, which is given by another explicit formula, which is underneath the blue one, and suddenly it becomes bigger. But actually, there was another spectrum called the tip spectrum in red, which is given by the domination for P negative enough of the tip of the curve. So this beta tip actually supersedes the blue one earlier than the green one. So in a way, this phase transition we have in this case again, in that case, actually is dominated by the tip transition. Nevertheless, so how do we unify all of these kind of results? By looking at the Q moments. Because now you can look at the generalization of these integral mean spectra in terms of P and Q, and look at the with the expectation of these mixed moments integrated on a circle of radius smaller than 1 diverge when you approach 1. And then you will have a spectrum depending on P and Q. The nice thing, for instance, is that it unifies both spectra, inner and outer spectra, because if you take this inverse map, which is 1 over f of 1 over z, it's going to give you we were in the inner case, it's going to give you the external whole plane map. So for instance, if you take now the moments of this inverted map, you are going to see that if you start with P here, you are going to end up with the inner map with P and 2P here. So it means that introducing this Q moment, P and Q moment, is a natural framework to deal with both with inner and outer whole plane SLEs. Right? And of course, this gives you the Bertrand map for Q equal 2P. But for Q in general, you will have a broader, a two-dimensional integral mean spectrum. So this is what we studied. And the nice thing also is that if you look at so we define this generalized notion of integral mean spectrum, so P and Q in general, in particular for the whole plane, and we look for this function beta of P and Q. But of course, if you look at what I call the m-fold transforms, Fm, which is the 1 over m's root of f of the m, if you integrate it on the units, you calculate the derivative, you have this kind of course, a formula. You look at the moments of Fm prime P, Fm Q, P modulus, you are going to find out that they are the same thing as the derivatives of f prime, the derivative of f and f itself at z to the n, to some powers which are a linear transform of P and Q. So it means that if you want to look at it means that all of these n-fold results actually are given by the result for the one-fold results, meaning in particular that beta m of P and Q is beta 1 of P and Qm, where Qm is given by this combination. And in particular, if you want to have the standard spectrum of the n-fold, so without Q here, Q equals 0, well, it's given by the spectrum of the one-fold in terms, simply if you take Q equals 0, here Qm will be P 1 minus 1 over m, so here, and here you will have P. So it means somehow the general notion of integral mean spectra is a proper one when you look at the n-fold. So what do we claim to be the case? So I mentioned this tip formula, so it means for SLE kappa, we have this tip formula, which I did not show before, which was valid for P negative enough. We have the Smirnov spectrum beta naught, given by this explicit formula, and up to P0 star, and this is the one we saw before. Now we claim with, in this work, that the whole plane SLE kappa generalized integral mean spectrum will be given by this formula, augmented by another formulation, which is in terms of P and Q. So you see that these ones do not depend on Q. Right? While here we have we are looking for a spectrum which depends on P and Q. And depending on P and Q, we have this beta 1 of P and Q, which is given by this formula. So we had this formulation before for Q equals 0. That was the green formula before. Now we have this explicit form. And we have to see when in the plane of P and Q values, these four spectra appear. So I'm not telling you exactly how we get this. We get it from this differential equation I had before, the Smirnov type, and which we have to generalize for values of non-zero values of Q. And so what kind of drawing do we have? Well, I skipped the way to do this. So I'm going to give you only the answer. So this is a PQ plane. Yes, this is a PQ plane. So you have so maybe some people just got lost. So let me repeat the function. So you have the tip. So this is for standard SLE. So this is something which corresponds to the bulk of the SLE. This is something which corresponds when you have this whole plane SLE. You have one tip at finite distance. So it locally provides a certain contribution to the integral mean spectrum given by this form here. And then there is a linear part which is for higher values of P, positive values of P. And now we have this function which depends on both values, P and Q. And so here you have so this is a standard P line. So in here you have Q. So what we claim is that if you follow the Q equals 0 case, so here you have the region where you have the tip dominating. Then there is a region here where you have beta 0. And then you have the special point, which is a transition point we had before, this P0 star, P star, where you have a transition to the linear form. This is a result of Belayev at Smirnov. But when you put a Q which is non-zero, then you move in this in the plane. So you have 4 domains. One where you have the tip, which is to the left of this value here. You have here a part of this parabola, the green parabola here, above which you do still have the bulk spectrum of Hawking SLE. Then you have a domain which is in this infinite wedge between 2 straight lines here, which I don't give you the equations of, where you have the linear spectrum. And here you have the whole region, and here you have actually it's a quartic, so you have a blue curve here, which supersedes this green parabola. Here we run a part of green parabola here, below which, so below this blue curve, below the green one, below this straight line here, you have the spectrum which depends on both P and Q, beta 1. And of course, this spectra, this function beta 1 and beta 0, all of these transition lines, all of the spectra match. So, you have 4 functions and they do match. So along all of these lines, they match. And remember that I said before, this result is valid for our problem, which is the interior whole plane SLE mapped to the slit plane. But remember I said that if you look at the original problem of Belayev-Smirnov, it was given in this generalized formalism, it was given by, I said here, since that was outside of the unit disk, this is inside. So I said that if you look at the moments of their outer map, they are given in terms of R moments for Q equal to P. So it means in terms of this drawing, that you have Q equal to P, which is a straight line here. And this is exactly what they obtained in their paper. They obtained that you had first, you had the tip, you had here the bulk, and then you became linear. But in their version, you never intersect with this domain, because actually, when you go to P negative, you are above this quartic, blue quartic, which I did not describe in more details. You can do it another way. You can. This is for our parameters for the inner map. If you look at the parameter of the outer map, you are here. And Belayev-Smirnov, they were working on this Q equals 0 line here. So they had these 2 points, so linear spectrum transition, the tip spectrum here. So they were living in this region where you do have the tip here, the beta 0 here, and the linear 1. While here we claim that if you look at Q, you have a certain domain here where you have, this is for M equal -1 in that case, for K equals 6, where you have a new spectrum depending on Q. And I will soon finish. So of course you can look at the M4, so I'm going to skip it. And you can finish with what is called the universal spectrum. So it's a well-known problem. It consists in looking at the supremum of all of these spectra. What is the biggest, the largest spectrum you can have in 2 dimensions for any kinds of conformal maps. And actually there are a lot of conjectures and results. And here, so they correspond to the standard case, which is Q equals 0. So these conjectures actually consist at looking at the line P, is the real line here. So, and there are the fact that for P, so there should be P minus 1 for P greater than 2. This is the result. Should be minus P minus 1, which is actually modulus of P minus 1, for P negative enough. Another result. And then in between, people don't really know, and they are very famous conjectures. And we have here at least one famous complex analyst, person who just spoke before, who knows much more about this. And actually, there are two famous conjectures. That the fact that Brennan's conjecture is that telling that somehow the transition between a certain form here, which we don't know, which might be p squared over 4, which to the transition to minus p minus 1 is at p equal minus 2. And the Kreiser's conjecture, which is that the form of the universal spectrum in between minus 2 and 2 is given by p squared. Now, we can ask the same question in terms of this generalized spectra for P and Q. What are the largest spectra you can have, in terms of P and Q? And so we claim that it should be the same thing as the usual spectra, depending only on P, except that in a certain domain you will have another universal spectrum which will correspond actually to the Köhler function again, which is 3P minus 2Q minus 1. So that's simple as this. And actually we can show it actually along this line. Actually we can show finally with Nogman done with the Carrier scalar that actually it is valid below the line. So of course if you say you believe in all of these conjectures, then you draw the separatrices and you find this a straight line here, a straight line here, a straight line here, another straight line here, and here a portion of parabola where you match p squared over 4 and 3p minus 2q minus 1. So you have this spectrum. But even so, even if Brennan and Kreiser's conjecture were not true, so you would not have this here, and this minus 2 maybe shifted somewhere else to some p naught, actually, still, this function will be valid underneath the universal. When you match the universal spectrum, you have, depending on them, that would be correct. So anyway, I think I should stop there.
Thank you very much. So there's time for this, please.
Yes, so the convergence of the asymptotic for the integral mean spectrum could indicate that the field of values f prime or absolute value of f prime, so the field of values converges suitably renormalized to some limiting field when the radius goes to 1. Have you investigated that?
No.
Or maybe the logarithm of that?
No.
Other questions?
Is there a simple geometrical interpretation of all those results?
What do you mean by geometrical?
Well, with the property,
I can guess, but
well, the geometrical properties of some aspects of fractal properties of SLE curves.
Well, there is a way to see it in terms of condensation. Well, there is a way to understand it heuristically, actually, from a condensation of. There is a way to look at this whole plane as kind of limit of the standard radial SLE when you expand your unit circle to infinity. And if you do that, and then you have a way to see it corresponds to the domination of what is outside of the SLE trace, which is mapped to infinity, actually, when you look at the whole plane SLE. So somehow along the circle there is a kind of condensation process. So you integrate on your circle near 1, and somehow when you raise your power p, suddenly there is one part of the circle which dominates everything. This is the transition. So somehow we have a way to understand it as a kind of condensation of the measure around these circles when you put 1. So this would be the answer. In terms of the fractal properties or whatever, the appearance of this new spectrum corresponds to what happens at infinity. So if you want, when you do the so you have the tip spectrum, which is what happens near the vicinity of the tip. There is a bulk spectrum, and then there is this kind of other spectrum which comes from infinity, and from the fact that the map is unbounded, which is cool. In the Bailey-Smith version, you have another tip, so it was when you do the inversion, this part is mapped near the origin. But in terms of the fractal properties, I don't really well, actually, I did calculate this spectrum in terms of f of alpha a long time ago, but I don't remember exactly.
Okay.
I would say still it corresponds to looking at something which is, when you look at the tip of an SLE, you really explore the tip and also the vicinity of the tip. When you look at these properties, In terms of tip, you really sit at the tip. Here you are at infinity, but in terms of tip, it's really something which happens at the tip. So if it's something we understand.
Other questions? Okay, this is not the case, so let me close the session by thanking Bertrand and in fact all speakers of today. Thank you.